Good morning. This is the first video lecture for CHEM 431B. It is for lecture number 8, which is for Friday, April 15th. Previously, we had talked about metabolism and the two subcategories, catabolism and anabolism. And we also talked about how you can have several reactions in such pathways, and those pathways are regulated by feedback inhibition. Today we're going to talk about a little bit more about coupling reactions. I had talked last time about how ATP hydrolysis can be coupled to endergonic reactions to make overall reactions exergonic. And we'll just go into some more quantitative detail on that. In a separate lecture, I will talk about how to solve problems 2, 3, 5, and 7a in the back of chapter 12. So let's get started. So we'll start off with a coupling. Reactions. And here is an example of one reaction where you have A going to B, and the delta G under standard conditions is going to be equal to 10 kilojoules per mole. And then we've got a second reaction. Of course, that's an endergonic reaction, the first one. And let's say you have a second reaction where you have C going to D, and the delta G for that is going to be minus 30 kilojoules per mole. Okay. And of course, in order to get these reactions to go in order to get A to go to B, if we could couple these reactions, that'd be great. And so we can just say A plus C will go to B plus D, and the delta G under standard conditions is going to be equal to 10 plus minus 30, which is going to give us minus 20 kilojoules per mole. Okay, so that's fairly basic stuff. And we can actually get into some more details about A going to B. So let's just take our first reaction again and analyze that a little bit further. So here we have A going to B, and as we said before, that's delta G under standard conditions of 10 kilojoules per mole. And this diacritic symbol, this first symbol here, represents a pH of 7.0, and this little plimsoll sign here represents that we have a temperature of 25 degrees Celsius. And for all standard conditions, also we start with 1 molar of A and 1 molar of B. Okay, so we have 1 molar of those. That's what we start off with. Once the equation, or once the reaction reaches equilibrium, we will not have 1 molar of A and 1 molar of B. We will have a difference. Obviously, we're going to have less B and much more A after this, because this is an endergonic reaction. we should probably write this as a reversible reaction, but we won't do that right now. Okay. So let's say that we want to know, what is the ratio of A to B. So let's say that's our goal here. Okay, we could figure that out. All we need to do is use this equation, which I talked about before, where you have delta G overall equals delta G under standard conditions plus the gas constant multiplied by the temperature in Kelvin multiplied by the natural log of what's called Q, okay? And that Q is the mass action ratio. And most of the time, that's the concentration of the products divided by the reactants. So I'll go ahead and rewrite this as delta G equals delta G under standard conditions plus RT, the natural log of the concentration of the products divided by the concentration of the reactants. Okay, so we want to know what the ratio of A to B is, and actually I'm going to make a caveat here. This is going to be at equilibrium. Okay. And at equilibrium, delta G overall equals 0. Okay. And so we can put that into the equation. 0 is going to be equal to delta G under standard conditions plus R T natural log of products over reactants and now all we have to do, in this case now that we have delta G equals 0 overall, then this becomes K equilibrium. So I'll rewrite it one more time. 0 equals delta G under standard conditions plus RT natural log of K equilibrium. So if I were to solve this for K equilibrium, I would take delta G under standard conditions to the other side of the equation, other side of the equal sign. That's going to be minus delta G under standard conditions equals RT ln of K equilibrium. And then I divide both sides of the equation by RT. That equals the natural log of K equilibrium. And then in order to get rid of this natural log in the mathematical equation, I just need to say take the power of, the base of E. And so that's going to be E to the minus delta G under standard conditions divided by RT is going to be equal to K equilibrium. And we know all these values. In our case, we know that it's going to be E to the minus 10 kilojoules per mole divided by 0.008315. That's the gas constant which has the units of kilojoules per mole multiplied by Kelvin, and times the temperature, which is going to be 298 Kelvin. That's going to be equal to K equilibrium. Okay, and when we figure that out, when we do the mathematics, put that in our calculator, that's going to be, K equilibrium is going to be equal to 0.0176, which is going to be equal to the products, concentration of the products, divided by the concentration of the reactants, which is going to be equal to B, concentration of B, over the concentration of A. What about, but we want to know what is ratio of A to B. All we have to do is take the inverse. So A over B, that ratio is going to be equal to 1 divided by 0.0176. And if I put that in my calculator, I get 1 divided by 0.0176. I get 56.8. So there's a lot more A than there is B, which is what you'd expect for an endergonic reaction here. So A will pile up. This reaction favors the reactants. We can even go further. We can actually figure out what is the concentration of A and B. Okay, we can even do that. And the reason why we can do that is because under standard conditions we started with 1 molar of A and 1 molar of B. So we know that no matter what, A plus B is going to be equal to 2 molar. Okay. So here we have 2 equations, and we have 2 unknowns. So you know from algebraic principles that we can figure out both A and B. So if I solve for B, B is going to be equal to A multiplied by 0.0176. So I just rearrange that equation there. Okay. And then I can plug this information. So I'll say this is 1, and then I can plug this information into here. And so I get A plus A multiplied by 0.0176 equals 2. A is going to be, we can pull A out of this equation. It's A multiplied by 1 plus 0.0176 is going to be equal to 2. So that means A multiplied by 1.0176 is going to be equal to 2, and A is going to be equal to 2 divided by 1.0176. And when I do that, I get 1.96 molar. which again makes a lot of sense. The concentration of A is going to be very high, very close to 2, because it's an endergonic reaction. And at equilibrium, and then I can figure out what B is, because I know that A plus B equals 2 molar. So actually, I'll just make this easier. It's going to be equal to 2. And so we have 1.96 plus B equals 2. So B is going to be equal to 2 minus 1.96, which equals 0.04 molar. So we figured out the concentrations of A, and we figured out the concentration of B under standard conditions, where we start off with 1 molar each of A and B. At equilibrium, we have a lot more A than we do B. And you can do the same thing for B going to C as a separate exercise. Okay. Let's go ahead and take a more realistic example. Chemists have been able to calculate what is the equilibrium constant for glucose 1-phosphate going to glucose 6-phosphate. Okay. I'm going to abbreviate this to make it easier to write. So we'll just abbreviate glucose as GLC, and we'll abbreviate the phosphate as, the phosphate that's bound to glucose as just a P, and we'll abbreviate this glucose as GLC 6-phosphate. Well, hello again. This is the second video for the coupling reactions lecture number 8. And we will continue where we left off. We had wanted to figure out how to go from glucose 1-phosphate to glucose 6-phosphate at 25 degrees Celsius, and the question is, what is K equilibrium? And what we're going to be given is a couple of reactions. One is glucose plus inorganic phosphate goes to glucose 1-phosphate, and the delta G under standard conditions is going to be equal to 21 kilojoules per mole. And we also have glucose plus inorganic phosphate going to glucose 6-phosphate, and the delta G under standard conditions is going to be equal to 14 kilojoules per mole. And we can couple these reactions so that we get glucose 1-phosphate going to glucose 6-phosphate. Let's see how we can do that. All we have to do is basically reverse equation number 1, chemical equation number 1. So I'll go ahead and do that. That's going to be glucose 1-phosphate goes to glucose plus inorganic phosphate, and the delta G value now gets reversed, so that's going to be minus 21 kilojoules per mole. And I'll go ahead and rewrite the second equation. Glucose plus inorganic phosphate is going to be giving us glucose 6-phosphate. And I'll rewrite the delta G under standard conditions. It's 14 kilojoules per mole. And we just cross out those molecules that are on both sides of the equation. So I'm going to cross out the inorganic phosphate. I cross out the glucose. So my sum here is going to be glucose 1-phosphate going to glucose 6-phosphate. And I just add these two values, and that's going to be minus 21 plus 14. That's going to be minus 7 kilojoules per mole. Well, that doesn't give us the answer yet. Remember, we want K equilibrium. But remember, I had solved for K equilibrium last time, and K equilibrium is going to be equal to e to the minus delta G under standard conditions divided by RT. And I have all this information from this. I'm going to obviously plug in this value into here, and I have RT, and I'll get the K equilibrium. And you can tell by looking at this, and you should do this constantly whenever you have these equations. You should say, okay, you know what? I know that my K equilibrium is going to favor my products, okay, in this case, because it's an exergonic reaction. So I know my delta G under standard conditions here is going to be greater than 0. Okay, I'm sorry. Say that. That was a mistake. Hold on. My delta G is going to be less than 0. Okay, so delta G is going to be less than 0. Okay, and as I said last time, one of the best coupling reactions is this one right here, where you have ATP. And I'll write in the charges here, which has a -4 charge plus water is going to give us ADP 3- plus inorganic phosphate which is has a -2 charge plus a proton, and the delta G under standard conditions is going to be equal to minus 30.5 kilojoules per mole. In many of the reactions that I showed you, water was involved either as a product or as a reactant. And the reason why we don't include water when we do our products divided by reactants, we don't include water here. And the reason for this is that the concentration of water is so high, we think it's high, at least in a test tube, that we ignore water because its concentration is so high. So its overall concentration does not change in the cell or in the body when we have these reactions that use water. So that's why we don't include water as one of our products or one of our reactants. Although, of course, we know that it is reacting, but it's because its concentration is so high, it doesn't count. I want to go over what I call tricks. Tricks that the cell uses to make endergonic reactions go forward. Okay. So the first trick is, I just said before, we couple the reaction with ATP hydrolysis. Okay. The second trick is what I call lowering the product concentration. And you might think, well, why does that help? It helps to understand the second concept. We look at the overall equation for delta G. So delta G is going to be equal to delta G under standard conditions plus RT ln, and we'll just say products over reactants. So analyzing this very carefully, you could see that if we were to lower this value right here, the products, okay, that's going to make this overall term negative, okay, and that could offset this value if it's positive. I'll just write a little positive sign there, so that the overall delta G, okay, is going to be less than 0. And that's what we really care about, this overall delta G, because that is what's actually happening in the cell. So if we could lower the product concentration, we can achieve the reaction, we can make the reaction continue to go forward such that the metabolic pathway can continue to go forward. What are some of the ways to lower the product concentration? Well, I'll just say A, the products become substrates for exergonic reactions. Let's take this example of A going to B. And let's say this is an endergonic reaction, so that most of the time you have the B going to A. Okay, that's favored, where B goes to A. However, if you've got a very strong exergonic reaction where B is going to go to C, okay, you can drive this reaction forward. Okay, so in other words, although you're making very little B in the beginning, eventually you can get the overall flow of the reaction, of the set of reactions, to go to the right here. So the products become substrates for exergonic reaction. This is an exergonic reaction. What's another way in which we can lower the product concentration? Another way is to move the products to another part of the cell. Okay, so for example, or in the body. So for example, here we have A, and again this is going to be going to B, but we'll say this is a very endergonic reaction. But as long as we can take that B, okay, and move it, let's say from the cytoplasm, and now B is going to be moved to the mitochondria. Okay. It's the same thing as lowering the effective concentration of B in the cytoplasm, so that overall this reaction will go to the right, and the reactions can continue to, the metabolic pathway can continue. So these are two of the tricks that the cell uses in order to cause the flow of the reactions to move towards their final destination. Okay, we'll stop right here. We've talked about coupling reactions. We've been able to add some numbers to this concept. We've shown you how to calculate the final concentrations of products and reactants if you know what the initial concentrations are. And I've shown you some ways in which endergonic reactions can be made exergonic by some tricks that the cell uses. Next, we will talk about a couple of problems in the back of chapter 12 that I think are illustrative. And in these problems, I'll give you some more information about how the cell can metabolize certain reactions and what are the controlling mechanisms for these. Okay, so that'll be for the next video. Thank you.